Hi, my name is Thomas Kim. In this session of video, I am going to implement Fast Modular Powering C++ implementation. I watched some YouTube videos about fast powering, modular powering algorithm. Most of the videos explain the theory behind, but they don't actually talk about implementation. In this video, I will implement fast modular powering using C++ implementation. It can be a little bit challenging actually, for especially those who are not experienced in bitwise operation. And also about Fermat Little Theorem and Euler's Theorem, also Chinese remainder theorem. I will talk about them in a few minutes later after explaining C++ implementation first. Then I will give you details about the C++ code. Before explaining C++ implementation, I need to mention bitwise operation in C++. This is byte, 1 byte, 8 bit. This bit is called least significant bit. Least significant bit. This bit is called the most significant bit. If we represent number 35 as binary digit, binary number, this integer 35 will be represented in binary digit like this. 1, 1, 0, 0, 0, 1, 0, 0. Effectively, it is something like this. Effectively, this is 2, 0, 1 times 1 means this number, 1 times 2, 0. 0 means this number, plus this 1 times 2, 1, plus 0, 0, 0, 1, 1 times 2 fifths, power of fifths. This number is actually, this is 1, 2, 32, makes 35. This is binary representation. If you are watching this video, you already understand this. Now I am talking about the shift operation. In C and C++, there is an operator like this. This is called right shift. Right bit shift operator. And if number 35 1, this operation means we shift every bit to right hand side 1 bit, then it becomes like this. The first bit, the zeroth bit goes up, and the first bit comes down here. This bit comes here, 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 and this bit falls down here. 0, 0, and 0 is inserted. This is the result of this operation. Okay, so if we assign like this, P is 35, P equals P shift 1. What it means is this side is actually this, and the result is actually assigned to P again. This operation can be written in one single operation like this. So you have to understand what it means. Bitwise shift. The result will be assigned. The bit of 35 binary digits are shifted on the right hand side. Then the result is assigned to P again. Another thing you have to understand is something like this. P and 1. This operator is called bitwise AND. Bitwise AND operator. What it means is something like this. For example, if I make a truth table like this, 0, 1, 0, 1, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 1, 1, 1, like this. For example, so if I make a summary, 1 and 0 is 0, 0 and 1 equals 0, 0 and 0 equals 0, 1 and 1 equals 1. This side. You have to remember this table or this operation. So if we want to get the first bit, for example, if we want to get the first bit, P is 35, and if we want to get this, the least significant bit, zeroth bit, we can say P and 1. Now let's see what it means. Number one is represented like this. 1. This is 1. This is P. If we end P and 1, will be something like this. P and 1. So 1, 1, 1, 1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 0. So effectively, this is P and 1 operation, bitwise operation. The result is something like this. If, for example, P is 1, 1. This is 2. In decimal number, this is 2. Okay, this is decimal number 2. Or 2. This is 4. 5. 5, for example. One again. If 5 ampersand 1 would give, this result will give 0, 0, 0, 0, 0, 0, 0, 0. This is 0. 5 and 1 gives 0. Otherwise, for example, this is 2. This is 2, decimal number 2. If 5 and 2 gives, this is 0, 1, 0, 0, 0, 0, 0, 0, right? This gives number 2. You have to understand this binary operation. So, bitwise AND operation. So, I explained operator something like this. What it means? It means the last digit, the last binary digit of P. Okay, we shift on the left hand side 1 bit and assign the result to P. Okay, and P ampersand 1. This means the last the least significant bit 1, the value of bit 1, either 1 or 0. The result is 1 or 0. Now I am going to explain how to evaluate 3 to the 35th power of mod 37. How we going to implement this algorithm in C++. Say note A is 3, P is 35 here, and N is 37, and B is initially, we will let initially 1. So we implement like this. While P, then we implement like this. Initially while P, and we change P here at this point, P here, P shift on to the right 1. Now let's try this first. Let's try this code first. Initially P is 35. And if we represent 35, 0, 1, 2, 3, 4, 5, 6, 7, in the bit binary digit, it becomes 1, 1, 0, 0, 0, 1, 0, 0. This is P0 is 35. Like this initially. At this stage, P is 35 like this. In the loop, P is shifting 1 bit to the right. Then it becomes like this. It goes up and it moves down to here. 1, 0 moves down to here. 0, 0. This bit moves to here. 1. Then it moves 0, 0, 0, like this. This is second state. Then it goes back. Then this value is still at 0 because 1, 1. This value is still at 0. Okay, so it falls down here again. Now it shifts once again. I would say this is P1, for example. Now it moves to P2 stage. Here it shifts once again. It pulls up. It moves down to 0, 0, 0. This bit moves here. It moves to here. 1, 0, 0, 0, 0. Okay. Then it returns here. This value is still not 0. Still not 0. This value is still not 0. So it goes down here again. It shifts once again. P3, it moves once again. It goes up. It 1, 0. It moves to here. 1, 0, 0, 0, 0, 0. Now it loops again. Then it moves to here. 0, 0, 0, 0, 0, 0. Please note that this is not yet 0. P4, P is still at 0, okay? So it loops again, P5. Now it goes up, it moves down here, 1, 0, 0, 0, 0, 0, 0, 0. It loops once again, but it goes down. If we shift once again, it goes up, right? It goes up, then remaining all zeros. So at this stage, it goes down, goes back, then it is 0. P is at this stage, P6 stage, P is 0. So it loop, it jumps out of loop. So you understand what this means, right? You have to understand. Another thing is, now we are introducing here another code if P and 1, then we introduce code block here. B times A, B A, and B modulo N. Now block close. At this stage, now here I add another code here. After this code, A times A. A times A, and A modulo equals N. Please watch carefully about the value of B, and the value of A. Okay? Initially, P is 35, and the first zeroth bit is 1. So this block runs when the value is 0. Okay? The last bit is 1. This is 2 0. 2 zeros is effectively 1 actually. Okay? I would say just 0. Zeroth bit value. Okay? Zeroth bit is 1. So it comes at this point. Initially A is 3, B is 1, so this value B becomes 3. B becomes 3, and it pulls down here. Initially A was 3, and A was 3. So at this point, after shifting at this stage, A becomes 3 times 3 at this point. Okay? And this bit is at this stage. So it goes back again here at this point. This is 1. Okay? So we record 1. For example, now it comes because this bit is 1 again, so this executes again. Now B was 3, okay? Previous B was 3, A is 3 times 3. So 3 times 3. This is new value of B. Then it comes down here again. It pulls down. It now shifts at this stage here. It pulls down. Since previous A was 3 times 3 times 3 times 3. Okay? Now it goes back again. If it goes back again, the value is 0. So this block is not executed. And it pulls down. This is the previous value, now times 4 times. 3 times 3 times 3 times 3. Okay? At this stage, it goes back here again. The value, this stage, the value is 0. Okay? So it doesn't execute, it pulls back because last digit is 0. Okay, it doesn't digit, it pulls back. Then A becomes again 1, 2, 3, 4, 5, 6, 7, 8, 3. It is 8 times 3 times 3 times 3. It is 8 times. So it becomes total 16 times. Okay, 16 times over 3. It becomes 316. Okay, this way it loops until when it becomes fifth time, when it becomes fifth time loop, then it is previous B times now A becomes 3 times 3 times 3 times blah blah blah. This is 32. 32 times over 3. 32 times over 3. 32 times over 3. So effectively 32 times 2 times 1 times. Okay? So effectively it becomes 335. Then it pulls down. At this point, lastly, this is this stage. Lastly, when it pulls down, it goes back. P becomes 0. This value becomes 0. So it pulls down. Then B effectively has 335. Note, each time we do modular operations like here. Modular operations, so it becomes mod n. Okay? So P is the result. This code looks very simple, but actually it's hard to understand if you are not accustomed to this kind of logic reasoning. I will make it clean. Try to picture it to your head. I will make a clean code. So we are making functions like this. int, fast mode, I would name fast modulo. Like this, A, P, N. Of course, these are integers. Then open curly brace. Initially, int, P equals 1. Initially. Then while P I said shift what? P shift equals 1. Okay. Then here if P and 1, this means last bit is not 0, then B times A. Now we have to modulo, we apply modulo N, B modulo N. Okay? Then we close this block. Here, A times A. Okay? Then we apply modulo again. A modulo N, A modulo equals N. This here, after the block, we are returning. Return B. B is effectively mode. B is actually A P mode N. The value, the return value. I hope you understand. I will call this function fast modulo. Now I am talking about the algorithm we just implemented. I would say underscore test modulo. It gets A P N like this. This solves this equation. Now I'm talking about Fermat's Little Theorem. According to Fermat Little Theorem, Fermat's Little Theorem, if A and P are coprime. If A and P are coprime, of course A and P are integers. A and P are coprime, then A to power of P minus 1 is congruent to 1 mod P. Okay? It effectively, when we are dealing this Fermat Little Theorem in cryptography or RSA algorithm, in fact, P is most of the time, this is prime number. Okay? P is prime number. And A can be any number. Since P is prime number, it can be any number. Because any other prime number, not P, is coprime. Right? So we can apply this rule. For example, say when we operate something like big numbers like 3, for example, 100, for example, like this, and we want to modulo, for example, 5, mod 5, for example, 5 is prime number, and this is prime 2, effectively. in such case, if we are using Fermat Little Theorem, since it becomes, now let's see, 5 times, let me see, 5 times, we have to say P, this is P, so this means P minus 1 means 4, effectively. So it means 4 is modulo 1 mod 5. It means, this theorem effectively means this. See, this is 5 minus 1 is 4 is modulo 1. Okay? So in case of 100, we can say like this, 4 2 8 5 25, right? So it can be written like this. 300 means 3, 4 times 25. 25? Yes. Then it means 3, 4 over 25 mod 5. It means 1 because of this. It means 1, 25 mod 5 equals 1. We can calculate like this. For example, it is 1 like this, then it becomes 1. It becomes 1 like this. Then it becomes 3 at this point. At this point, 3, 4 times 25 times 3, like this. This is effectively 1, 3 mod 5. We can calculate like this. This is what actually Fermat Little Theorem means. So if we have a P, we will make it into C++ code. If we make it to C++ code, we can make it like this. So it can be represented like this. A, P, mod n. If n is prime, for example, if n is prime, we can get, for example, n prime, that n minus 1. Okay, so this number can be represented like the A. P can be represented P Q times P, Q times n minus 1. N minus 1 is this is prime number right now. Then plus we can say R. Okay, remain R. This is P. This is P. Okay, so this value does not matter because in this case it becomes A Q times n minus 1 times A R, like this, and it effectively becomes 1, and this R is actually remainder. R is remainder. P modulo n. Okay, so it effectively becomes A P modulo not n minus 1. Okay, n minus 1. So n minus 1 mod n. So once we calculate this, then we apply this rule to here. this is how we use Fermat's principle. Okay, I will make it as a function. Okay, so I will name it Fast Modular Fermat, like this, and it gets A, P, N. Here N should be prime. Then it can be like this. It can be like this. Return. We are calling this function Fast Modulo. We are calling this function. N is the same. Okay. Then P becomes P modulo n minus 1 n. Or we can make it modulo 2. We can make it modulo 2 like this. I will talk about it later. Or we can just do like this. Then we are applying Fermat Little Theorem. We first make this algorithm. Then using this, we can apply Fermat's algorithm when n and a are coprime. But more correctly, n should be coprime. N should be prime. When prime, then we can apply like this. This is actually modulo, remainder. We are applying this theorem. And now I am talking about, this is Fermat's. Now I am talking about Euler's. In case of Fermat's theorem, this P should be prime. But what about if it is not prime? Then we use Euler's Totient function, Euler's theorem. According to Euler Theorem,
You have new mail.
for every integer a and positive integer a and n, a phi n congruent to 1 mod n. Okay? This is Euler's theorem. Here, n does not need to be prime. N does not need to be prime. Okay? So n can be multiple of P and Q, multiple of 2 primes. In such case, if P and Q, if n can be factorized to 2 primes, P and Q, here, if n can be factorized 2 primes like P and Q, then totient function becomes like this. PQ is n actually. It becomes P minus 1 times Q minus 1. Okay? This is totient function. So if we apply this here, it becomes like this. A, P minus 1, Q minus 1, congruent to 1 mod n, where n is P times Q. Okay? This is actually what Euler's theorem says. Now we are applying this rule, this Euler's theorem once again to here. Okay? How? It's easy. Say, if you remember, when we use Fermat's function, we implemented it like this: Fast Modular Fermat like this. Return. We are calling this test modulo. Here, A is the same. At P, we say P modulo m minus 1 n. We call it like this because this is the remainder. We are doing the same to here. Now, instead of this, we are saying, I would say not PQ, I will say ST. Because it conflicts with this. ST, okay? Like this. Then we can say, we can make Fast Modular Euler like this. Fast Modular Euler. A, P, N. Then this function is very simple. Very simple. Return Fast Modulo. Here, A is the same. And this part is very simple. P modulo P S minus 1 T minus 1. Now this side is just N, PQ. Here N is S times T, and S and T are prime. Okay? Because only when S and T are prime, this holds. Totient function pi n pi, if it can be factorized P and Q, for example, like this, then it becomes P minus 1, Q minus 1. There are lots of YouTube videos about the totient functions on YouTube, so you can look at those videos. And in this video, I'm explaining how to implement Fast modular operation. So there, however, I said Fermat Little Theorem, Euler's Theorem. There is another one. There is another Chinese remainder theorem. About Chinese remainder theorem, I will talk in next video. Now I will move my desktop and I will implement these into Fast modular C++ code. I will build on my previous video, a source code from my previous video, Diophantine equation C++ program. If you want to follow with me, please download this source code here. Then I will copy this code and move to my working folder. This is actually my previous code. I will save it old and copy it here. You download the code. I start Visual Studio. Open Diophantine equation. The previous solution. I will add one more project here. I will say Fast Modular I created an empty project. I'll make it a startup, empty source file, Fast Modular Powering. Now here include IO stream, include CSCD INT, template, type name T, I will name it T underscore fast modular. I will say fast modulo. T A T P T N. Now here T P equals 1 while P if P and 1 P times A P modulo N. Here P 1 A times A modulo N. Return B. The code is this simple. Now we are testing NT mean STD cout test modulo 3 35 37. Now let's run it. It should give 25. Okay, it's working correctly. See, if you are unsure, so please watch these videos and you can say samples. I actually tried this one. By watching this video, you can get more information. Please watch this video, Fast Powering Algorithm by Jeff Suzuki, and also refer to Fermat Little Theorem by Noureddin Sadawi. This man's video, also about Euler's Totient function. Please watch this video. Here, if we move, we can get more samples. For example, let's try
25 down this.
Let's try 4, 50, 19. Four, 50, 19, 17, the result. Now check the result here. Seventeen.
And there's my final one.
The result is 17. 17. So this fast modulo works perfectly. Now we are moving to Fermat Little Theorem. Template, type name T. I would just say fast modulo like this without underscore. I just changed my mind. Type name T, fast modulo. This is Fermat. T A T P T N. A over P mod N, where N is prime. Fermat Little Theorem. Now we can do the same thing. For example, R is remainder, P modulo n minus 1. This is actually remainder. Then we can call Fast modulo. A is the same, A. Then R remainder, then n. This is Fast Modular Fermat Theorem. We can try it actually. Please watch Fermat Little Theorem example by Math with J. I will use this sample 2 to 50 mode 17. I will copy it. Fast modulo Fermat 2 50 17. Now we are calling this Fast modulo Fermat. This should be prime number, and while we are executing, the result is 4. Here the result is 4. So my algorithm is correct. Now we are moving to Euler's Totient function, Totient theorem, using that. Fast modulo, I would say Euler. I would say n, but say we have to say t, st, like this. I will say a power p mode n equals s times t. Okay, so according to Euler's theorem, we are defining tr, we are defining the same way like this: p mode s minus 1, this is totient function, times t minus 1. I would say t by totient function would be s minus 1 times t minus 1. So it becomes like 5. We are interested only the remainder. Now we are calling fast modulo again, fast modulo here, A. Instead of P, we place R remainder, then we say S times T, this is N. Now we are calling fast modulo using Euler's theorem. Now it's done. Now I will find some samples. Here again, Euler's theorem, Fermat theorem, and discrete logarithm by Stephen Gordon. In this video, 97, 97, 121, mode 147, 143 actually means 11 times 13. So we will adopt that. I say Euler (97) 121 11 13. Now run, Control F5. Sorry, we made a typo here. Now okay, Control F5. 97.
To solve a problem.
See, the result is 97.
The power of if we have a prime
Let's see.
mod 143. So it works.
97, the result. So the result is 97. So this way we implemented a fast modulo powering modulo powering using this method, and also we implemented the Fermat Little Theorem, also Euler Theorem, and there is another method that is Chinese remainder theorem. Using Chinese remainder theorem is also important for fast modulo powering operation. I will in next video I will talk about Chinese remainder theorem. I will post this source code to my web YouTube, and you can download this sample source code in the link down below. Thank you for watching. Please don't forget subscribing my channel. Also give me like button if you like my code. Thank you for watching.